Welcome. In this mini lecture, we're going to cover the key ideas from sections 210 and 211. We're going to begin in section 2.10 with negating statements. When we negate a statement, we want to rewrite it so that it has the opposite truth value of what it originally had. So if the statement was originally true, we would want it to be false, and vice versa. So let's consider some examples. All Martians are short and bald, or my name is not Princess Leia. In order to make this have the opposite meaning, we don't want it to be all Martians, we only need there to be one. So our statement would become, there exists a Martian. And rather than being short and bald, we want our Martian to be tall or hairy. So there exists a Martian who is tall or hairy, and my name is Princess Leia. Remember from De Morgan's laws that change and statements to or and vice versa. That still holds when we're negating statements. Now let us consider there exists a fast tortoise. So rather than having there existing a fast tortoise, we would need all tortoises. And rather than being fast, they would be slow. So in this case, if we were to write this in symbolic logic, our original statement would be, there exists an X such that X is fast, where X is tortoises. Now, when we negate our statement, we would have the negation of there exists an X such that X is fast, which would be logically equivalent to saying for all X, the negation of X is fast, which when we think about that in terms of common language, the opposite of fast is usually meant to be slow. So we would arrive at, for all X, X is slow. So we've looked at two examples now of negating statements. And what we can conclude is that a for all becomes a there exist, and a there exist becomes a for all statement. Let's look at one more. Everything that is cold is ice cream. Here, our statement we can consider as for all X, and then if X is cold, then X is ice cream. Which we can further break down to, for all X, P of X implies Q of X. Now, we're interested in the negation of this statement. So let's consider for a moment the truth table. Looking at our truth table, recall that true implies true is true, true implies false is false, false implying true or false implying false is also true. So when we negate the statement, the only time it is true is when we began with a true implying a false. Now, this happens to be logically equivalent to P and not Q. So if we consider that, let's verify that this is in fact logically equivalent. So if P is true and Q is false, we would have a false. If P is true and Q is true, we would have a true. If P is false and Q is false, we would get a false. If P is false and Q is true, we would also get a false. So looking at these two columns, we can see that, in fact, these two things are logically equivalent. And that's usually how we will write the negation of an implication. So, if we're going to consider P and not Q, our negation will become, rather than for all, we will have there exists an X which is cold and X is not ice cream. This is a very usual convention in mathematics, and we'll use it to prove a lot of things. So make sure that you understand that the negation of an implication can be expressed as P and not Q. So again, recapping, if P of X is an open sentence with variable X, then the negation of a for all X, P of X, is equivalent to there exists an X such that not P of X, and the negation of there exists X such that P of X is equivalent to for all X such that not P of X. Lastly, in 2.11, there are three logical inferences that arise a lot in mathematics, and we will use often when proving statements. The first of which is modus ponens, where we have P and P implies Q. That together implies and guarantees that Q is in fact true. For example, if you can buy alcohol, then you are at least 21 years old. Jane can buy alcohol. That allows us to conclude that Jane is at least 21 years old. Modus tollens takes our conditional statement together with not Q, not the conclusion, to ultimately determine that not the hypothesis must follow. So for example, if you can buy alcohol, then you are at least 21 years old. Fred is less than 21, hence Fred cannot buy alcohol. And then lastly, the law of syllogism. P implies Q and Q implies R allows us to conclude that P must imply R. For example, if you watch football, then you drink beer. If you drink beer, then you eat pizza. Hence, we can conclude, if you watch football, then you eat pizza. That's all for now. Thanks for listening.